So we've been talking about polarity of bonds so far, but now let's talk about polarity of molecules. So let's go ahead and draw these two. I've got carbon tetrahydride, right? And I have so in both cases I have shapes that are tetrahedral. I have, in this case I have all the same atoms on the outside. In this case I have 2 chlorines and 2 hydrogens. Now you might look at this in 2 dimensions and say, looks pretty symmetrical, hydrogen on each side, chlorine on top and the bottom. But if we look at this in a, if we look at this here, this is what we have. This is CH2Cl2. And what you can see is the chlorines are much more electronegative than the hydrogens. So this is a polar molecule. It is not symmetrical, as opposed to the I think it was CH4 that we had, perfectly symmetrical. So a tetrahedral shape is a symmetrical shape. It's got 4 evenly spaced atoms attached. But if any one of these 4 is a different atom, you're going to have a polar molecule. Okay? This will be a polar molecule. But if I have all the same things on the outside, it's going to be perfectly nonpolar. And that's because any other, in this case carbon tetrachloride that comes out this one, is not going to see any part of this molecule that looks any different, any more or less positive. Okay. So this is nonpolar, and this molecule will be polar. All right, let's take a look at another. Here we have ammonia. Common name is ammonia, or proper name would be nitrogen trihydride. Okay. So what I have here is I have 3 attached atoms. I got 4 total domains. This is a trigonal pyramidal. And remember, I don't see this lone pair up here, but they do act on pushing these guys down. So I end up with a shape that looks like this. More like a pyramid with these electrons sitting up here. So again, I can look at the NH3, and this is what I have. So because I've got lone pair of electrons up here, it's going to be very negative on this side, the blue side, compared to the hydrogen side, which is going to be more positive. So if I look at the molecule like that, what I have clearly is a polar molecule. And because trigonal pyramidals always have this lone pair of electrons up here, trigonal pyramidals, regardless of what's attached, is always going to be a polar shape. Always. So this is polar. Okay, now let's take a look at H2S. Whoops, let's just make that a bond like that. Now, if we look at the chart on shapes, we've got 1, 2, 3, 4 domains, only 2 atoms attached. So this is going to be a bent shape, right? So what I actually have is this. Okay, these electrons that I don't see, electron pairs, are pushing down on the hydrogens. So this is going to look like it's going to look like this, right? So again, I have lone pairs of electrons up here. It doesn't matter whether I have 1 or 2. It's going to be more negative up here than it is down here where the hydrogens are attached. So a bent shape, just like trigonal pyramidal, will always be polar. It's always going to have the lone pair. Whenever I have a shape that has a lone pair sticking out on the central atom, I have a polar molecule. Alright. So this will also be a polar molecule. Both polar molecules. Okay, so we know water is a polar molecule. The electrons are more closely held on the oxygen side, making it more negative. Okay, so what I'd like you to do is do some practice on the bottom of page 9 and the top of page 10, and then go back to page 6 and identify if the molecules are polar or nonpolar. Check your answers. The answer key again is on Moodle, and then you'll be ready for an exit pass or a quiz. Okay, I'll see you for our last podcast.